Hello and welcome back. We are going to look at a problem involving the steam tables and steam. So it says that there is a closed rigid vessel which contains 1 meter cube of steam at 7 bar and 500 degrees centigrade. Okay, so we have some vessel of some kind. It has 1 meter cube of steam. So the initial volume is 1 meter cube. We are dealing with steam. The initial pressure is given as 7 bar, that is 0.7 megapascal. Initial temperature is 500 degrees centigrade. The steam is now cooled to a state where the pressure is 0.5 bar. Okay, so we have cooling, some heat is being taken out. The final pressure is 0.5 bar, which is 0.05 megapascal. We are asked to determine the temperature at which condensation may first occur, the fraction of the total mass that will condense, and the volume occupied by the saturated liquid at the final state. Okay. So we are cooling this. It initially contains steam. We don't know what phase it is in, but since it says it is going to start condensing, this must be in superheated phase, so that later on there is some liquid. We are asked to find out the temperature at which it will condense, the fraction which will condense, and the volume occupied. So let us try to sort of plot this on a T versus V diagram maybe, and try to find out what it shows. So our initial condition is 0.7 megapascal and 500 degrees centigrade. So let us try to see where that is. So I have the steam tables here. So we want 0.7 megapascals, if I remember correctly. So we want 7 bar is 0.7 megapascal and 500 degrees centigrade. So 0.7 is between 0.6 and 0.8. So at 0.6 megapascal, the saturation temperature is 158 degrees centigrade. At 0.8 megapascal, it's 170. So at 0.7 is going to lie between these two, and the temperature we are given is 500 degrees centigrade, which is much higher than either of this. So we must be in the superheated region. So from the superheated region, we are going to come to this saturation condition. Okay. So let me go to the superheated tables. I want 0.7 megapascal, which is again not here, but I have 0.6 and 0.8, and I am at 500 degrees centigrade. So I am going to look at these values over here. Okay. So what I know is that at this condition, the specific volume is 0.5920 meter cube per kg for 0.6 and 0.4433 meter cube per kg for 0.8. So I can take the average of these two as the value at 0.7. So I have 0.5920 and 0.4433. So this is going to be my specific volume at 500 degrees centigrade and 7 bar, which gives me a specific volume of 0.51765 meter cube per kg. So this is my specific volume initially. So I can now plot it. So I will maybe do that in a minute. But I have the specific volume. I also have the volume completely, which is 1 meter cube. So I can find out mass. I know that the specific volume, I know that V1 is V1 by M1, which means mass is this. So that's 1 by which gives me a value of 1.93 kilograms. So this is essentially the mass of steam which is initially here. So what I can do now is draw the 0.7 megapascal isobar which goes something like this. What I can also do is, so we are at some specific volume of some 0.5 at a temperature of 500 degrees centigrade. Okay. I know that the temperature at the critical point, which is this point, is about 374 degrees centigrade or so from the tables. So, what I can do is I can look at the tables. So, this is the critical point, it is about 373 degrees centigrade. So, I know that 500 degrees centigrade is higher than that. So, let me draw, for example, the isotherm at 500. It goes like this. This is the isobar at 0.7 megapascal. So, I do not have enough space here. So, I am going to maybe draw this a little steeper. What I want to show is that the point which we have, which is our state 1, which is the intersection of the isobar at 0.7 megapascal and the isotherm at 500 degrees centigrade. So, this is my initial point. So, if I now start cooling, the mass of steam I have completely in this vessel is fixed. So, mass is constant. I have a rigid vessel. So, the volume is constant. So, because m is constant and v is constant, small v is also constant. Therefore, in this process I have specific volume being constant or essentially an isochoric process. So, if I cool this, what happens is it undergoes a temperature drop at constant specific volume. So, that means my process will happen like this, and finally, I will reach some point here where it will first start condensing. So, I am asked to find out the temperature at which condensation will first occur. So, condensation will first occur at this point. So, if I can draw these things graphically, I should be able to find out the values. So, graphically I know that this is that point. So, graphically what this shows me is that this is an intersection of a point where the specific volume is 0.5176 meter cube per kg and the saturated vapor line, because it is this point. So, it is on the saturated vapor line. So, since I can do this graphically, I should be able to find it by tables. So, what I want from the tables now is a point on the table where if I look at the Vg values, the Vg is equal to this value. So, now that is what I am going to do. I am going to look at the tables and search for some entry where Vg is about 0.5176 meter cube per kg. So, I need Vg is 0.5176 meter cube per kg. So, let me look at all the values here. So, this is my Vg table. So, I have a value here which is about 0.5085. So, it lies between 130 and 140 degrees centigrade. So, what I can also do is, let me look at, this is the temperature table. Let me look at the pressure table and see if there is a value closer to what I want. So, over here Vg is this column over here. I have 0.6 and I have 0.4, neither of which is especially close. Okay, since I am looking for the temperature, maybe I will go back to the temperature table. So, I want 0.5176, which lies between these two. So, it is actually it will be very close to 140 because 1.51 and 130 is 0.66. So, it is going to be very close to 140 degrees centigrade. If I want an exact value, I can of course interpolate between these two. So, I can tell right away the value is close to 140, but maybe I will interpolate anyway and get a better estimate. So, I have 0.6680 at 130 degrees centigrade. So, at 130 degrees the specific volume is 0.6680. At 140 degrees it is 0.5085. Okay. So, if I want the actual temperature, I can do something like T minus 130 by 140 minus 130. should be the corresponding value 0.5176 minus 0.6680 by 0.5085 minus 0.6680. So I can now calculate this out. So I think I get the value as 139.42 degrees centigrade if I have done this correctly. So what I see is the temperature at which condensation may first occur is very close to this. Because in reality what we see is that for condensation to occur they may require some degree of subcooling, but if I assume that condensation occurs instantaneously as soon as saturation is reached, then this is a condition at which condensation will occur. What I am also asked to find out is the fraction of the total mass that will condense. Okay. So what we see is when I go from here to here, at this point it starts to condense. So the temperature is 139 degrees centigrade. The corresponding pressure we can see from the tables. So we are looking at these values. The pressure here is about between 0.2 and 0.3 megapascal, okay, which is about close to 3.6 bar, because our temperature is 139 degrees centigrade, which is close to 140. So the pressure at when it first starts to condense is close to this value. So this is about 0.36. So if I was to take this as 140, then the corresponding pressure here would have been about 0.36 megapascal or 3.6 bar. I will say approximately this, because I have not calculated the exact value. I can do that, I can interpolate and calculate, but approximately this. But we are continuing to cool it till the final pressure becomes 0.05 megapascal. So it means what we are doing is we are continuing to cool it till we reach this value. So what we want now, sorry, this will continue to be a horizontal line till we reach the edge of this, and then it goes there. So what we want now is this point over here. We want to know the fraction of total mass that will condense. So essentially what we want is the quality at this point that will tell us how much is in vapor fraction, and the remaining we know is what is condensed. So we want the vapor fraction where the pressure is 0.05 megapascal and the specific volume is 0.5176. So let us go to the 0.05 megapascal condition. So at 0.05 megapascal, what I want is Vf, I want Vg, I know V is equal to, I have calculated somewhere, 0.5176. So I can generally write V as either 1 minus x into Vf plus x into Vg, or Vf plus x into Vg minus Vf, which then tells me that x is this. So I want to find out the value of x. So I need Vf and Vg at this condition. So I am looking for 0.05 megapascal saturated conditions because it is within the vapor dome. So let me go over here. This is the temperature table. Let me look for values by pressure. So pressure table, I want 0.05. So I have 0.04 and 0.06 here. So 0.05 is in between those. I want Vg, so Vf is 0.001026 and 0.001033. by interpolation. Essentially I want values at 0.05 bar, which is halfway between 0.04 bar and I want values at 0.05 megapascal, which is halfway between 0.04 and 0.06 megapascal. So I use this, and similarly for Vg, the value is, I will take average of these two. I have 3.993 and 2.732. So let me calculate these. This is 1.0295 into 10 power minus 3. This is 3.3625. So I can now substitute those into this formula here and find out the value of x. So V is 0.5176. And I have Vf is 0.0010295. That's my numerator. I have Vg is 3.3625 and I have Vf is 0.0010295. So if I do this, I get the quality as 0.1536. So what it means is that my diagram is not very good because the quality is fairly low. So the way I have drawn it, of course I have not drawn this steep enough, so this point must be somewhere around here, not somewhere around here. So I know that now, which I did not know before I drew it. So if I was to now draw it like this, maybe this point is somewhere here, so that when it intersects I have some value, and then finally over here this is about 15% and this is about 85% by mass. Okay, so this is the quality. So I know that x is essentially mass of vapor divided by m. So what I want to know is mass of liquid, which is mf, that is m minus mg. So x is this, or mf is also essentially 1 minus x into m. So I have 1 minus x is 0.846 and my total mass we calculated some time back as 1.93 kg. Okay, that is, where was I? 1 minus which comes out to be about 1.63 kilograms. So this is the quantity of liquid which I will have when I come down to this condition from 500 degrees centigrade to this condition. We are also asked to find out the volume occupied by the saturated liquid at the final state. Okay, so we are asked how much will this liquid occupy. So we know that Vf at this final state is this. So volume of liquid we can find out. So the total volume is known, which is 1 meter cube, which is I think what was given over here. So the final volume of the entire system is known. What we can find out is essentially we know also Vf, which is we calculated over here as 0.001025 meter cube per kg. We also know the mass of the liquid, which is 1.63 kg. So, the total volume of the liquid will be essentially mass of the liquid into specific volume of the liquid. So, that is 1.63 into this. We will get some answer in meter cube. Which is 1.67 in 10 power minus 3. Okay, so this is 0.0295, which means my (1.67 10 power minus 3 meter cube). So, I think I wrote it here incorrectly initially. So, this is the final volume. What we can also find out is what is the final temperature. We know that the temperature, we know that this final point lies on the saturated region, and the pressure over here is 0.05 megapascal. So, what the temperature here would be the saturation temperature at this condition. So, at 0.04 the saturation temperature is 75.9, at 0.06 it is 85.9. So, at 0.05 we can take it as essentially the average of these two. Okay, 75.9 and 85.9. So, that should be essentially 80.9 degrees centigrade. That should be the temperature at this condition. Of course, that was not asked for, but that is also something we can find out. So, what we see is that this steam condensed. So, out of the total mass of 1.93 kgs, we have about 1.63 kilos in liquid state. We have the remaining of about 0.3 kg in vapor state. But if you look at the volume, the total volume is about 1 meter cube. The volume of the liquid is 10 power minus 3 meter cube, 1.67 10 power minus 3. So, you have 0.3 kg of vapor, which occupies almost the entire 1 meter cube, and you have 1.6 or kg of liquid, which occupies 10 power minus 3 meter cube. So, we do know already that, for example, the liquid density is 10 power minus, the liquid specific volume is of the order of 10 power minus 3, which means the liquid density is about 1000 kg per meter cube, whereas the vapor specific volume is about 3, which means the vapor density is 1 by 3 kg per meter cube. So, there is a factor of about 1000 at least in difference between the specific volumes and densities of the liquid and vapor. So, a large mass of liquid occupies a tiny volume, and a small mass of vapor occupies a large volume, which is very clearly visible over here. So, that is what this problem says. Thank you. Okay, so let us go on to another problem. We have here a problem which says determine the specific volume of water at 20 megapascal and 400 degrees centigrade in meter cube per kg using steam tables, the ideal gas equation of state, and generalized compressibility charts. So, we want to find out this using all these three methods. So, steam tables is rather easy to do. We have 20 megapascal is the pressure and temperature is 400 degrees centigrade. So, let us find out whether this state is saturated or subcooled or superheated by looking at first the saturated tables. So, I have 20 megapascals, which is here. The saturation temperature for this is 365 and the temperature here is 400. So, T sat at 20 megapascal is 365 degrees centigrade from the tables. The actual temperature is 400, which is greater than 365, so it must be superheated. So I need to look at the superheated tables for a pressure of 20 megapascals. So let me go to the superheated tables. So I need here pressure is 0.6, 0.8 and so on. This is up to 2. So let me go on to the next page. So I need a pressure of 20 megapascals. So this is that. And I have a temperature of 400 degrees centigrade, which is this. So what I want is the volume. So that's 0.00995 meter cube per kg. So from the tables, V is 0.00995 meter cube per kg. This is in superheated region. So the first part is done. So the next is to find out this using the ideal gas equation of state. So if I was to use the ideal gas equation of state, I have PV equal to mRT, or if I take this m below here, I have PV by m is RT. This is small v. So V is essentially RT by P. So that is R is the universal gas constant divided by the molecular weight. So that's 8314.5 joule per kilomole Kelvin divided by molecular weight. So this is H2O, this is 16 plus 2, this is 18 kg per kilomole. This is R. The temperature is 400 degrees Celsius. So I have to add 273 to this. So I have 673 Kelvin divided by pressure is 20 megapascals, that is 20 in 10 power 6 Pascal. So this will give me the specific volume using the ideal gas equation of state. So I get this value as 0.01762 meter cube per kg from this calculation. So what we see is that the actual value is 0.0099. If I use the ideal gas equation of state, I get a value which is more than twice or about twice that value. So we can see that it is pretty inaccurate to use the equation of state under these conditions. So assuming that water vapor, even in the superheated region, when we assume that it is behaves like an ideal gas, we would be making this error, which is one of the reasons we are looking at these tables. So the next part is to look at what answer we can get for this using the generalized compressibility charts. So as we remember from the charts, we have values of Z versus PR and TR. So I am going to find out the reduced pressure, which is essentially pressure by critical pressure, and the reduced temperature, which is essentially temperature by critical temperature. So the pressure is 20 megapascal. The critical pressure we have from the steam tables, that is essentially this value. So that's 22.064, also in megapascal, which gives me a value of 0.906 for the reduced pressure. For the reduced temperature, I need the critical temperature, that is essentially 373.95 degrees Celsius. I am going to convert it into Kelvin, and on top I have the temperature as 400, which gives me a value of 1.04. So what I need to do now is find out Z from the tables, and then I have the ideal gas equation of state, which is corrected to say that PV by RT is not equal to 1 but is equal to Z. So I need to find out Z, then I know that PV by RT is equal to Z if I use the compressibility charts. So V would be essentially Z times RT by P. I have already found out RT by P, so essentially I have to multiply whatever value I got earlier by Z. So I need to find out Z, and then my volume would be the Z times this value earlier which we found, which will give me my corrected value. So I need compressibility charts for this, so let me find out those charts. which were on the slides earlier which we discussed. Okay, I have here now the compressibility chart which we used earlier. So, what I need now is to look at these charts for a reduced pressure of 0.9 and a reduced temperature of 1. Okay, so reduced temperature of 1 is this here. I need a reduced pressure of about 0.9, which is somewhere here. So, my correction is about 0.2 is the value of Z. If I am somewhere here, correction is about, let us say this part is a fairly steep. So, I am not going to get very accurate values from this. So, if I was to, for example, look at it a little more accurately. So, if I was to draw a line here, this line would possibly go somewhere like this. So, if I am very close to these bottom curves, because the curve is very steep, depending on where I draw that line, I could easily get a lot of error, which is what we see. But if I was to draw this line a little more straight, it would possibly cut somewhere here. That looks fairly straight, I think. So, I think I would get a value of about 0.5 or so for Z. Of course, I do not have markings on this particular chart on the x axis, which is making it a little more difficult. If I use the proper chart which had the markings there, it would make it easier. But let us say I get a value of say about Z is about, I do not know, 0.47 or something, or 0.5. Let us take Z as 0.5. So, Z from the charts is coming to about approximately equal to 0.5. So, if I was to take this as 0.5, then what I get is value of this is I get is as 0.008, which is much better than this, but still not very close to this. So, if I use charts which are magnified a lot better and found out the actual values, I would get values which are somewhat close to the values which I get from the steam tables. So, what we see is that this is much better than using the ideal gas equation of state, but if we had the tables, we would prefer to use the tables rather than do this. But since I need tables separately for each gas and I may not have those tables, if I do not have that, I can use these charts and still get better estimates than by just using the ideal gas equation of state. So, that is essentially what we were trying to do here.